Bismillahirrahmanirrahim. So now we are uh, going over lecture number 17 of this online series of lectures. We were talking about second moment of area in the previous lecture. At the end of the previous lecture, it was not yet complete, so we can briefly go through about the second moment of area, and then we can solve one example on this. So the second moment of area, it is about x-axis it is y square dA, and about y-axis it is x square dA. The first moment of area is integral x dA, which gives us integral x dA divided by the total area, that gives us the x coordinate of the centroid, and integral y dA divided by the total area, that gives us the y coordinate of the centroid. So that was the first moment of area. Centroid is the first moment of area in which we have first power of x and y in the integrals, and in second moment of area we have the second power of x and y. Ix is going to be y squared dA, that is the second moment of area. And similarly Iy is equal to x squared dA. Polar moment of inertia, as we discussed in the previous lecture also, it is going to be the addition of the two, x square plus y square, x square plus y square. As you can see here in the figure, it is equal to r square. So Iz is equal to integral r square dA. That is the total moment of inertia about, or second moment of area about point O. Now the formulas for second moment of area about the centroidal axes are given in the tables in the books of mechanics. I would just like to talk about this transfer of axes. Transfer effect axes, if we want to find the second moment of area about an axis which is not passing through the centroid, the standard formulas that we have are for the second moment of area about an axis which is passing through the centroid. However, if we wish to find, this is the proof, we are not going into the proof of this, but if we are to find the second moment of area about an axis x which is parallel to the centroidal axis in x direction, this is also x direction, but this one is passing through the centroid, and this is also x direction, but this is about an axis which is parallel to the x-axis passing through the centroid. So whatever is the formula for the second moment of area passing through the centroid about x-axis, we are going to add plus a times d squared. A times d squared. So d is the perpendicular distance between these two axes. The x-axis about which we are finding the second moment of area, and x-axis which is passing through the centroid. So the perpendicular distance between these two is d, dx you can say. And similarly for the y-axis, if I bar y is the second moment of area about y-axis passing through the centroid, then about a parallel y-axis which is not passing through the centroid, so it is parallel to y bar axis. So this is going to be again equal to I bar y plus a d square, where dy square is the perpendicular distance between this y-axis about which we are finding the second moment of area, and the y-axis which is passing through the centroid. So this is known as the parallel axis theorem. So in this manner we can find the value of second moment of area about any axis. This is the parallel axis theorem. These are the formulas derived for different types of shapes. This is for a rectangle, and as we discussed in the previous class also, that this I bar x is equal to 1 over 12 bh cube. B is the base and h is the total height. For the rectangle, the centroid is going to be at the middle of the rectangle, so x naught axis or x bar axis is this, and this is the y bar or y naught axis. These are the centroidal axes, and if we want to find second moment of area about this x, this is the proof of the formula. We can find second moment of area like this. Well, this involves double integration, which you have probably not yet studied, so we will not talk about the derivation of this. So this bh cube by 12, this is the second moment of area about x axis, and about y bar axis, which is passing through the centroid, it is going to be hb cube by 12, hb cube by 12. So these are the formulas for the case of a rectangle, and if we are to find the second moment of area about this x-axis and this y-axis, then according to parallel axis theorem, we are going to add ad squared to the second moment of area about an axis which is passing through the centroid. So ix bar plus area of this rectangle times the perpendicular distance between x and x naught, which is h by 2. So a into h by 2 square, and a is equal to b into h. So we can substitute that, and it will give us I bar x is this, so ix is this here, ix is here, this is ix bar about x-axis passing through the centroid, and plus area b into h is the area, and h by 2 is the perpendicular distance between the two axes, x and x naught, and square of this, a into d square, I bar plus a into d square. And in an identical manner we can find the value of iy. It is not found here in this example, in this simple problem. This is the case of a triangle, and we have found the value of second moment of area for this. And similarly other shapes are discussed. We are not going into these many details. So let us look at one example in which we calculate how do we calculate the second moment of area of a composite shape in which we do not have a regular shape. Mostly we will be talking about, in the courses of mechanics, mostly we will be talking about rectangles. So you should know the formula for second moment of area for a rectangle, that is bh cube by 12. Now let us look at this example. This is not from your book, this is from some other book. Say we have this cross section. This is the cross section of some beam, and we will talk about beams in our course of mechanics of materials. that is going to be in your fourth semester. So this is just the cross section, and we want to find the second moment of area about the centroidal axis. Now we know, again, just as we have done in the case of, in order to locate the centroid of this region, we have done in we have done earlier in the previous two lectures. We have located the centroid, so we will divide the geometry into two regions. One is this rectangle 1, and this is another rectangle 2. So we have two rectangles, so we can find the area of each rectangle. This height is 20, this is 90, area of this is 1800, area of the second one, this height is 40, this is 30, area of this is 1200, so the total area is 3000. Now location of y bar, we will select some reference. Say we select this x-axis, which is the base of this cross section. We select this as the reference, and we calculate the moment produced by the area vectors of different regions about this reference, which is the base. In most of the cases we will be selecting the base. So we will just see what is the difference, what is the distance of the centroidal axes of each regular shape from this reference. So centroidal axis of region 1, which is a rectangle, so it is going to be at the middle, so its distance from the base, which is the reference that we are taking, so this distance is this 40 plus half of this, which is half of 20, 10, so y1 bar is 50 mm. Similarly, y2 bar, the second moment of area, the location of centroid for the second region, again this is a rectangle, so it is going to be at the middle, and this height is 40, so the vertical dimension is vertical distance for the centroidal axis for this region 2 from the reference that we have taken, this distance is 20 mm. So 50 and 20 are the in the courses of mechanics we will be interested to know second moment of area about an axis which is horizontal axis on the cross section, because the when we will study beams in the course of mechanics of materials, we will see that about this axis the beam is going to bend in most of the practical situations. So we are interested to know the second moment of area about a horizontal axis which is passing through the centroid on the cross section. So this is the cross section of the beam. So we have located the centroid. The centroid can be found from here. We take the product y bar into a, so these are the two results. We take this summation, and this summation a y bar divided by summation a gives us the location of the centroid. So this is y bar is equal to 38 mm. So y bar is 38 mm from with respect to the base. We have taken moments about the base, so the location of the centroid is also going to be with respect to the base. So it is going to be 38 millimeters above the base. So it is just below the start of region 1. Region 1 starts at a height of 40 mm, so it is located here. This is 38 mm from the base. So we have located the centroid, and now we come to locating the centroidal, calculating the second moment of area. Again, the second moment of area we are going to apply now after we have located the centroidal axis, we need to calculate the second moment of area of this region 1 and this region 2 about a horizontal axis which is passing through the centroid. Now after we have located the centroid, we know the distance of the centroid from the top surface, from the bottom surface, from any reference we can find the distance of the centroid. So we would like to find the distance between the centroidal axis of region 1 and the centroidal axis for the complete cross section. This C, where we have x prime, this is the centroidal axis of the complete cross section. So we can find the distance between region 1, centroidal axis of region 1, and the centroidal axis of the complete cross section. So I1 bar is going to be equal to BH cube by 12, as we have seen. So I1 bar is equal to BH cube by 12. B is this. For region 1, this is the region 1 rectangle at the top. So this dimension is 90. So B is 90, H is 20. H is 20. So B into H cube divided by 12. This is I bar for region 1. And since we have to find second moment of area about a horizontal axis which is passing through the centroid, so we add plus AD square. A is the area of region 1. Area of region 1 we have already calculated, it is 1800 millimeter square, multiplied by D square. D is the perpendicular distance between the two axes, centroidal axis passing through the centroidal axis of the region 1 and centroidal axis of the complete cross section. So the perpendicular distance between these two is 12. So A, which is 90 into 20, 1800, this area of region 1, into D square. D is 12. Similarly, the second moment of area of region 2 about a horizontal axis which is about the centroidal axis, horizontal centroidal axis for the complete cross section passing through point C. So the second moment of area for region 2 about its own centroidal axis is going to be BH cube by 12. This is a rectangle, so formula for rectangle is BH cube by 12. Now B is 30 mm. For region 2, B is this. So B is 30 mm and H, which is the height, that is 40 mm. So 30 into 40 cube divided by 12. This is the second moment of area for region 2, rectangle 2, BH cube by 12. And this will give us second moment of area about the centroidal axis for region 2, which is this horizontal axis passing through this point. Centroid of the rectangle is going to be at the middle, so this is the axis about which we have this BH cube by 12 second moment of area. Now since we have to find the second moment of area about an axis which is passing through the centroid of the complete region, complete cross section, so we have to find about this x prime axis. So again we are going to use the parallel axis theorem. So whatever was the second moment of area for this region 2, which is BH cube by 12 plus A into D square. A is going to be for this region 2 area is 30 multiplied by this height, which is 40. So this is the area, plus D square. Centroidal axis for region 2 is going to be at the middle, which is going to be 20 millimeters from the base. Total height is 40, so it is going to be half of that. And centroidal axis for the complete cross section is 38 millimeters from the base. So the distance between this centroidal axis of region 2 and the centroidal axis of complete cross section is vertical distance is 18 millimeters. So plus A into 30 into 40 was the area into D square. So this is this second moment of area of region 1 about the centroidal axis of the complete cross section, I bar plus AD square, and similarly this is the second moment of area of region 2 about the centroidal axis of the complete cross section. So adding these two gives us the total second moment of area about an axis, horizontal axis, which is passing through the centroid of the cross section. So that is how we calculate the second moment of area for a given cross section, which is not a regular shape, but it can be divided into a number of regular shapes. So we can stop here this lecture. We can stop.